How are you guys all doing?
I'm all right.
Good.
Doing good.
Everybody still hanging in there?
Yep.
Good. I want to begin by asking you if you have any questions about the regression homework.
I have a question.
Somebody said something and I didn't catch it. Karen?
Hello.
Yeah, did you say something?
Yes, I did. I have a question about the homework.
Yeah.
So I ended up missing the last few classes. Looking at the homework, I turned it in. I only used one method. I used a simple regression that I did. I created a slope and did SS regression and residual followed by the ANOVA table. I was just wondering if there was actually another specific method that was supposed to be used, or if all the questions were similar to each other and their solution.
No, they're all similar to each other. It's just once again to make sure that you know how the process is working.
Okay, good. Well,
Yep.
I created a graph in Excel and checked my answers against Excel's equation and R squared, so I think it went well then.
Okay, good. Yeah. Yeah, regression isn't that complicated in terms of the calculations that are involved.
Mm-hmm.
Other questions about regression? So Karen checked her work in Excel. You could also easily put any of those data sets into R and run a regression on those things in R, just like you could do with anything else we've been doing in here. I finally got around to posting. Well, I finally got around to posting the regression report on Moodle. So if you guys could go to Moodle, to the Applied Stats folder, it's in today's materials. So it would be April 26th. There's a folder called Linear Regression Report. There is a set of instructions and two data sets, actually the temperature data and a data set called HTBC data.csv. And so if you would open up the regression report, somebody just groaned.
Dr. Klowinski, that was
Yeah.
me, I was testing my audio. Okay, so for my homework, everything went well, but I found myself in a p-value of 0. Is that possible?
Yeah, what generally happens when you put anything into a p-value calculator is that when the value gets below a certain level, like it's just so astronomically low that it's not worth really calculating, most calculators will return to you a 0. In R, this appears as 2.0 times 10 to the minus 16th. Whenever you see this in R, it's basically R's way of saying it's 2 times 10 to the minus 16th, which is a p-value of 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
That's hella small, yeah.
This is your p-value. So you'll see this in R a lot, this 2 times 10 to the minus 16th, and it's just like the p-value is so astronomically low that we're not going to try and even give you what the value is. It's less than this, and if it's less than this, you really don't have to think about it. Whatever it is that you're seeing is significant.
Okay.
And so
Thank you.
so if you put your F's F statistic into like Daniel Soper's calculator, if it returns to you as 0, it's basically saying the same thing as 2.0 times 10 to the minus 16th in R. It's just a astronomically low, what some people would call it, diminishingly low p-value. So,
Okay, thank you.
yeah, so if you go to the linear regression report instructions, I'm asking you to do a couple of things. So you're still dealing with this idiot who works on geckos and doesn't know anything about statistics. And he keeps giving you these data on temperature because he doesn't really know what to do with them. And so you've already looked at how body temperature varies across populations and seasons. And it appears that there's a spider on my desk in my office. It appears that, sorry, I don't mean to make you dizzy, but I just had to kill a spider crawling across my desk. All right, so it appears that geckos in the winter in both populations have colder body temperatures than either population does in the summertime. And in the summertime, the differences aren't that big. When you did the two-way ANOVA on this, you found the significant interaction, which is what that interaction is telling you. In the summer, they both behave one way, and in the winter, they both behave differently, but they behave differently in winter in each population. That's the nature of the interaction. So in thermal biology, anybody studying the thermal ecology of a species, there are some species that are ectotherms. They get their body temperature from their environment. But in spite of the fact that they get their body temperature from their environment, they're still capable of maintaining a relatively constant body temperature because they do what we call behavioral thermoregulation. They run into the sun when they're cold, they run into the shade when they're hot, and you can put a thermocouple inside of them that will measure their temperature constantly. And what you find is that while they're active, they can actually maintain their body temperature at quite high temperatures and at a relatively constant temperature over their activity period. Geckos are interesting from a thermal biology perspective because they're nocturnal. They don't have the opportunity to behaviorally thermoregulate. They're out at dark, so if they're too cold, they can't just run into the sunlight and warm themselves up. And so evolutionarily, most people who think about the thermal biology of lizards, which is a surprisingly large number of people around the world, we think of geckos as being less good at regulating their body temperature. So they are oftentimes referred to, as your researcher here tells you, they're referred to as thermoconformers. They tend to have body temperatures that conform to the ambient temperature because they don't have the opportunity to behaviorally thermoregulate. So this guy has been studying these geckos, and he has all of this body temperature data, but he also has wall temperature data. And so when a gecko is on the wall, oh man, I cannot draw today. When the researcher would find the gecko on the wall, the researcher would measure the body temperature of the gecko and then would measure the body temperature on the wall right next to the gecko. If the gecko is thermoregulating, is actively thermoregulating, what would you expect the correlation between wall temperature and body temperature to be?
The same.
If they are thermoregulating. If they're thermoregulating, they're moving around on the wall, but when they're cold, they're going to run someplace where it's warm and warm up, and then they might move to a colder place and hang out, but their body will still be warm. If they're too hot, they're going to move from a hot place to a cooler place to try and cool down. So their body temperature should be relatively constant while all around them what's happening to the environment.
It's changing.
It's changing. And so would you expect there to be a correlation between wall temperature and body temperature? Or would you expect there to be not a correlation between wall temperature and body temperature?
I mean, I guess if if body temperature is always constant, then there would be no correlation, right?
Yeah, so if you had a thermoregulating lizard, it would have a relatively constant body temperature, and regardless of where in the environment you happen to run across it at that moment, it may match in some cases, but in many cases you would expect it not to match. And so you wouldn't expect a tight correlation between wall temperature and body temperature. If, on the other hand, it's a thermal conformer, what would you expect?
What Grace said.
Exactly. You would expect that as wall temperature increases, body temperature would increase. Not only that, would you expect that to be a sloppy relationship or a tight relationship?
Depends on how good the gecko is, I guess. And
But depends on how poor the gecko is. If the gecko is really terrible at thermoregulating, its body temperature is always going to be what?
air temperature.
It's going to be tracking the temperature of the environment around it. And so you would expect this to be a very tight relationship with a high R-square value. And what would you expect the slope to be?
Positive.
But specifically, what would the value of the slope be?
1.
It would be a slope of 1.
So is this gecko wanting to achieve a set temperature, or he's just going with whatever?
So
temperature?
so normally lizards and frogs and things like this, well, lizards in particular and snakes in particular, they have a preferred temperature that they would prefer to operate at. And one of the things about geckos is they tend to have a lower preferred temperature than diurnal lizards. So while most diurnal lizards would like to have their temperature up around 35, 37, something like that degrees centigrade, geckos oftentimes have preferred temperatures down in the 20s, 23, 25 degrees centigrade. So they tend to have lower preferred body temperatures, but one of the ideas about why they have lower preferred body temperatures is because they don't really have many opportunities to raise their body temperature much above that, because they tend to be thermal conformers. And so they have a different physiology altogether in terms of how they alter their physiological capacity with changes in temperature. If you get these guys up at 35 degrees and race them down a racetrack, they are blazing fast, but they never get the opportunity to be that warm, generally speaking. And so if you test them down in their preferred temperatures and in kind of their normal operating temperatures, down in the mid-20s in terms of degrees centigrade, they're still pretty fast, but if you crank up their heat, they get much, much faster. So they're capable of taking advantage of warmer temperatures. They just generally don't, because they don't live in an environment where they don't have a set of habits that allows them to function. And if you take diurnal lizards and lower their body temperature to the body temperatures that you normally find geckos active at, their locomotor performance is much impaired by just going down like 10 degrees centigrade. And so nocturnal lizards tend to have a wider range of capabilities. I have taken these lizards in the lab down to 10 degrees centigrade, which is pretty freaking cold. and they are still capable of running, which most lizards in the world would have already lost their ability to turn themselves over. One of the ways that you test the thermal limits of a species is you put them in a room and you slowly lower the temperature. And as the temperature comes down, their body temperature comes down. And you occasionally take them and flip them over on their back, and you see if they'll flip themselves back over. This is called loss of righting response. And the loss of ability to right themselves after they've been flipped over. And at that point, you're effectively dead, because if a predator comes across you in nature and you're on your back because you're cold and you fell out of your tree or off of your wall or whatever, and you can't right yourself and run away, they're going to kill you and eat you. This is of import. Let me go and find this. This has happened a couple of times in the last couple of years. I'm going to share my screen with you guys. So here is a story from NPR. When winter hits. Yes.
I'm sorry for interrupting you. When is the report due?
It's on the Moodle site. It is due a week from Wednesday, so that's May 6th.
Okay, thank you.
So here are lizards that are just like hanging out, like laying on the ground, because they have gotten so cold in the Florida winter that they can no longer turn themselves back over. And that effectively renders them physiologically dead, because they have also lost their ability to escape from predators. And in this case, it looks like people are catching them and grilling them up, which I've never had grilled iguana, but I really don't ever want to. So the question that this researcher has is, are they thermoconforming or are they thermoregulating? If they're thermoregulating, they're behaving in a way that is atypical for a nocturnal gecko. And if they are thermoconforming, it's kind of what we would expect. But in order for them to be thermoconforming, you should expect a relatively high R-square value between body temperature and, in this case, wall temperature. And you should also expect to see a slope at or close to 1. If the slope is greater than 1 or the y-intercept is greater than 0, then they're thermoregulating to a certain degree, because this would ultimately, if this was a slope of 1, you would expect this slope of 1 to be centered at the origin. So the y-intercept would be, if you cool a lizard down, if you make the environment 0 degrees, you should expect body temperature of the lizards to be 0 degrees. And so it may be that there is a 1-to-1 relationship, that the y-intercept is somewhere up here around 10 degrees or something like that. In which case they're tracking the environmental temperature, but their temperature is 10 degrees higher than you would expect it to be. So there are a couple of things that you can test with the regression between body temperature and wall temperature to determine whether or not they are indeed thermoconforming. And so you have a data set in Moodle that basically has body temperature with paired wall temperatures that then allow you to test this idea. Now, this guy is curious, so on an ancillary note, he also noticed that when he was picking up these geckos in the field, it seemed like the geckos in Galveston were much smaller and thinner than the geckos in Oklahoma. And so he brought some of them back to the lab, and he measured their weight as soon as he got back to the lab, and he measured their body length. And he is interested in knowing whether body condition is different between these two populations. Body condition typically in herpetology world is the ratio of body mass divided by snout vent length, the distance between the tip of their snout and the base of their tail. tails break off in geckos, so tail length isn't a good measure in any lizard actually for body size, but snout vent length is the standard measure. So we would generally measure mass divided by SVL. This is body condition index, and then people in the past have analyzed that. What's the problem with analyzing that? Just calculating body condition index and comparing Galveston to Oklahoma City. This is an analysis of covariance sort of question now.
Ooh.
Why not just do this division, get this index, and do an ANOVA on that index?
Wait, what was the SVL?
Snout vent length, distance between the nose and the base of the tail.
Okay.
So it's mass divided by length. So think of BMI in humans. When you go to calculate your BMI, which is a measure of how overweight you are or not, it's basically a measure of your total mass divided by your linear length. And the heavier you are per unit length, the heavier the larger your body mass index gets. So similar thing going on here. Why would you not want to do this?
Could be other things influencing the body mass.
Well, not really. That's all the lizard really has is, I mean, he's not carrying a backpack or anything.
No, I mean like their gender. I mean.
Oh yeah, so certainly gender could be an issue as well, but what's the general problem with doing this? With calculating a ratio?
Oh, you lose something.
You don't lose anything. It just, let me go back. Let's see. Can you guys still see my screen?
Yep.
Whenever you're doing something where you use body size to correct a measure of interest, you can analyze those data without correcting it, but what's the other thing you can do? You can also calculate the ratio. When you calculate that ratio, though, you still get the same result in many cases as you would by analyzing the data unaltered. And it's because that ratio doesn't really serve as a very good correction for body size, and it gives you a different answer if you basically take the regression into account. And so we saw from last Friday that when you take the ratio, it doesn't necessarily correct for the issue at hand. In this case, the ratio gives you a totally wrong answer. In this case, there is no regression between body size and the variable of interest. So correcting for body size actually makes the larger things, the larger organisms, look different than the smaller organisms because you're doing that division. So it gives you an answer that is once again not accurate. In this case, the ratio, this is the variable of interest, this is the ratio. Dividing by body size doesn't tell you that these individuals are actually smaller at a given body size than these individuals, but you have two body size measures, the two ranges of body size measures that don't overlap, because in reality, the dark points are lower than the open circles. So ratios just mess you up. Once again, these guys look bigger than these guys, but because there's a regression that defines the relationship between the variable of interest and measure of body size, you're dividing these values up here by larger values of body size, but that still makes them larger when you take the ratio, when in reality, they're not different at all. So whenever you look at ratios, you have the possibility of reaching the wrong conclusion because ratios are just poorly behaved from a statistical standpoint. They don't necessarily give you the answer that is the correct answer. And so what this guy is wanting to do is he just wants to know is, does body mass differ between the two populations in terms of our Oklahoma City geckos, Edmond, Oklahoma geckos, heavier per unit length than Galveston ones are? And one way to do this is just to calculate the regression for the Galveston geckos, calculate the regression for the Oklahoma geckos, the regression of mass regressed onto body length, and then examine those two regressions to see if they are different. And so this is a regression assignment, and so you need to use linear regression to analyze these things. And there are two data files for you to do that. The first one is the temperature data file, which you've already had some experience with. You notice that for the two-way ANOVA, there appeared a second column that was wall temperatures. That second column appeared because that data set is now going to be used for a regression. And then the other thing, the other data file that you have, well, why am I in animal behavior? The other data file that you have is called HTBC data, which is stands for Hemidactylus tursicus body condition. It gives you the season that the individual was collected, the species, whether it's in Oklahoma City or whether it's in Galveston. So we have winter Oklahoma City, we have winter Galveston, we have summer Oklahoma City, or summer Galveston, and summer Oklahoma City. And we have a bunch of columns of data. One of the columns is the sex of the individual, whether it's a female, whether it's a male, or whether it's a juvenile. Then we have the snout vent length, and then we have the tail length. We have whether or not the tail has been autotomized, and then we have the weight. Obviously, you don't need all of these columns to do this task. What you basically need is when it was collected, what population it's from, what's the snout vent length, and what's the weight. And weight is the response variable in this case, and snout vent length is the predictor variable. If you know the length of a lizard, how well can you predict its weight? And does that prediction vary depending on where you collect it and when you collect it? And so you're going to be doing quite a lot of regression analysis on this project, which is why I've given you a week and a half to work on it. I'm not going to give you any further instructions in terms of how you divide up the data to do this, et cetera, et cetera. These are things that you should be working out for yourself. If you have questions after you've attempted to work it out by yourself to a certain degree, drop me a line and we can chat about it on the phone or on a Zoom meeting or however you want to do it. But those are the data, and these are the questions that the researcher has. Questions about that? Okay, so on the Moodle site, let's go to Moodle. Where did Moodle go on my computer? Oh, I navigated away from Moodle. You're still on seeing my screen, correct?
Yep. Yes.
Yeah. So here's the linear regression problem set and Athos right there. It says due 29th of April, 2020. No, that's the problem set. The linear regression report assignment is due 6 May 2020. It's right there in the description. You can see it without even opening it up. So, and then the last thing I want to share with you is something that Tom made that he sent to me last Friday because Tom has too much time on his hands. But this is an analysis of covariance printout that he prepared, where he took that R script that I posted and basically went through it, and he has the entire analysis down here because he likes seeing things in front of him, and this is an easy way to see things in front of him, and he thought that you guys might benefit from it also. So this is a printout of the thing that I'm about to go through with you, and also a thing that is on a screencast on the YouTube site. That's what we're about to go through. So you can download that and have it handy for you, or you can open up the R script from the Moodle site from last week, which is in the April 22nd materials, the ANCOVA example and the ANCOVA example CSV file. And if you want to have that open in front of you, you can just walk through it while I walk through it myself. Questions? All right. Unfortunately, I had a little choking incident on Friday after I left you guys, and so my throat is a little raw. So I'm sorry for the scratchy throat, but I am getting over having almost choked myself to death on my own saliva for whatever reason. Have you guys ever swallowed saliva and it goes down the wrong tube and you feel like you're going to die?
Yep.
Oh my gosh.
Yeah, that happens like almost every other day for me.
So it's pronounced when you don't talk to anyone all day. And so you sit at your computer for 3 hours working on things, and you just kind of forget to swallow, and then it creeps down your throat, and before you know it, you think you're going to die. And I actually went into a coughing fit so severe that I couldn't actually speak the rest of the day on Friday. I couldn't have my meeting with my animal behavior students because I literally couldn't talk. And so anyway, I'm still a little scratchy from that. So here's the R script. This R script is not how you would want to run an analysis of covariance. This is an R script that is written to kind of walk you through what analysis of covariance is doing and why it's doing it. So as a result, we're going to use a lot of packages that we wouldn't normally use. But the packages that you would normally want for an analysis of covariance are the CAR package. Compute ES and effects are two packages that are used to calculate effect sizes. And they're necessary in here because I'm interested in calculating effect sizes to make some graphs that we make. ggplot2, of course, you could replace this nowadays with tidyverse, because tidyverse is now a part of the ggplot2 is now a part of tidyverse. So you can just load the whole thing and be done with it. HH is a package that you can use to do post hoc comparisons after things like an analysis of covariance. Same thing with multcomp. And then, of course, you need RMNISC to do things like symbol calculations. So the first thing you want to do is load these up and install them if you haven't already installed them. So everything is there. You see that when I did the tidyverse, it loads Tibble, tidyr, readr, dplyr, forcats. It loads well, I thought I'm pretty sure that ggplot is in there somewhere. I'm not sure why it's not appearing. I guess we'll find out in a few minutes. So the ANCOVA example.csv file is the data file. It's a really small, simple data file. It's got the placebo group, the drug group, the memory scores, and then IQ. We went through this briefly on Friday. But basically, the question that the researcher has is, does a drug that he is proposing to give you improve your ability to remember things But of course, memory is a mental task, and so memory may vary by overall intelligence level. And the IQ test is one not great way of measuring IQ, of measuring intelligence, but it's a way of measuring it. And so they're using IQ score as the covariate. So always make sure that your classification data, your classification variable is actually giving you a classification rather than treating it as a number. Shouldn't have been a problem in this case because placebo and drug are both text. So you can, I always just like to get a look at my data before I do anything else. And so when you look at the data, when you run summary SE from the RMISC package, it breaks down your data into treatment, drug. There are five observations of the drug, 5 observations of the placebo. And it looks here like the drug actually does improve memory score, whatever memory score is. You also see that it has fairly large confidence intervals around the mean, but still the difference is much larger than the confidence intervals in this case. So in an imperfect world where all you ever learned how to do was an analysis of variance, you would look at the memory score, you would test to see if it varies between the drug group and the placebo group, and you would get an answer. And so what you see in the ANOVA table is that you see the sums of squares for the group, whether it's the drug or the placebo, and you see sums of squares residual. These are both around 73 or 74. And we can basically say, okay, well, what are the means? Well, the means are right there, but we can also use our analysis tools, and we can get what the fitted values are. And the fitted values in this case are just the means. They're the predicted values. That's 8.36 for the placebo and 13.8 for the drug. And once again, this is an output, but any output you can add to a data frame by just saying, give it a name, put it in this data frame, DAT, and put those values, which you had just saved up here. So you've made an object pred, and you want to put the predicted values in there, and the predicted values in mathematical terms are always y hat. So there's a little diacritical mark above it. That's why I call it y hat. And so now we've added y hat to our data frame. So now we have everything we need to have to make a graph where we are going to plot how score is correlated with IQ, and we're going to be able to graph onto that plot what the average values are before adjusting them using ANCOVA. So this little stretch of plot down here, and you can see I originally made this script up before I started doing common theme statements, and you can see now why I use common theme statements, because there's that much code that I don't have to redo every time. So basically it's going to plot IQ on the x-axis, score on the y-axis. It's going to color the dots and the lines by group, whether it's the drug or the placebo. It's just going to make a simple scatter plot at this point. I've got some other lines in here that have been commented out because we're going to be adding them as we go. So you run this, and it gives you this plot. And so you can see that as IQ increases, so does memory score, and it increases whether you are in the drug group, which is the pink dots, or the placebo group, which is the blue dots. And that tells you that you should probably be using an analysis of covariance. Now, we can show this plot with the means and with the residuals plotted. So I say we can do that. Why is it not wanting to do it? Oh, there it goes. My computer is just slow this morning for some reason. So here you have the average value for the drug group. Here you have the average value for the placebo group. But one of the things that you notice about this is that for some values, the residuals are quite high. And that's why the sum squared residual value is so high, is because by just doing an analysis of variance, you're ignoring variation due to the regression between memory score and IQ. When you ignore that variation appears in the residual portion of the analysis of variance. Yes.
Can you explain that again?
Yeah, so this is just the mean of memory score for drug, the red line. This is the mean memory score for placebo. But normally you could look at this and say, well, these are correlated with one another. But when you just do an analysis of variance, you don't take that correlation into account. So what that does is it increases the residual variation, the amount of variation that is not explained by the difference between drug and placebo. So you see these big residuals. The residual is the difference between the average value and the data point. Average value and data point, average value and data point. And in some cases, that residual value is really big. In other cases, it's smaller. For the placebo group, some cases it's really big. In other cases, it's really small. In this last case, it's really big. That contributes to...
Wait. So it doesn't matter if the data overlaps because they're from different means. So we're not looking for to analyze this variation.
I'm not sure what you mean.
I mean that we're not searching for variations within means, just among, right?
Yeah, so an ANOVA, with any analysis of variance, you're interested in what is the effect of drug versus placebo. So you're interested in comparing means. But as always with ANOVA, one of the things that gets in the way of you being able to see those differences is how much within sample variation there is. And in this case, the within sample variation, if you ignore IQ, the within sample variation is really high because of these residual values. And what we want to normally do is we want to do things in a way that it reduces the amount of variation due to unexplained factors, which is what residual variation is. So in this plot, there's variation that is accounted for by the difference between drug and placebo. So drug and placebo define some of the variation in the overall data set. But within drug, there's a lot of unexplained variation. Within placebo, there is a lot of unexplained variation. Some of that unexplained variation, though, is explainable because memory score is correlated with IQ. Wouldn't it be nice if we could remove that unexplained variation and explain it? Take it out of the residual variation category and put it into something like a category for regression. And that's what analysis of covariance is attempting to do. Does that make any more sense?
Yes, it makes.
It may make a little more sense in just a minute. So hang with me, and if it doesn't, we'll backtrack.
Yeah,
Okay.
I'm getting there. I'm getting there.
Okay. So in my comments in the code here in the script, it says, so there's a lot of residual, and if only I could spell, a lot of residual variation due to the correlation of the response variable with covariate. This is quantified in the sum-squared residual from the ANOVA table that we generated below. So what we want to know is this truly unexplained variation, or can this variation be explained by something else? Well, I'm now going to plot a regression line for both of these groups. So I've added a regression line to the plots that we've just made. And when we get plot 3, what you see with plot 3 is the same graph that we had before, but now it has the regression for memory score versus IQ for both the drug group and the placebo group. And you see that if we can account for that, the residual variation between the data point and the line, 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 and the data point and the line here, that variation that is unexplained is now much lower than it would be if we didn't account for that variation. So the horizontal lines represent the means of the two groups without accounting for variation in IQ. The line, as we've talked about with regression, is the running average of memory score as it varies with IQ. So this line here is also a type of mean. But it's a mean that changes. It's the mean of memory score as memory score is affected by IQ. And so if we can use those regressions to reduce the amount of residual variation because it's systematic variation, then we should attempt to do that. And that's what an analysis of covariance actually does. So by accounting for the regression model, we should be able to significantly reduce the unexplained variation in memory score, i.e. the sum squared residual. I don't know why I have mean squared residual in my commenting. So how we do this, we just alter our analysis code here. So we have been working with analysis 1. So analysis 1, I'll just type in right here. So the formula for analysis 1 is score as it's influenced by group on this data set. So now we're going to get score as it's influenced by both group and IQ. And when we do this, it gives us a different ANOVA table. And it now has a group category, an IQ category, and a residual category. And I'm going to do analysis 1 right underneath it so that you can see these two in combination. Because what you'll see is the residual value for the single factor analysis of variance is 73.03. This is the sum of squares residual. And in the analysis of covariance, you see that IQ, sum of squares IQ, is 52.12. Sum of the squares residual for the analysis of covariance is 20.91. What we've done by doing an analysis of covariance is we've taken some of the variation that was not explained in the analysis of variance. But that variation isn't really unexplained. It's a variation due to the fact that the response variable is correlated with a covariate. And so we can take that residual variation and say how much of that residual variation is actually due to this correlation, account for that variation, which then leaves in the residual category truly unexplained variation, not systematic variation that we can explain. That reduces the residual value, residual sums of squares, so that when we then test the main effect that we're interested in, which is group, which in this case is 73.98, we're now dividing that by a much smaller number, which then allows us to see the effect of group more clearly because we have removed some of the noisiness of the data, because the data aren't noisy as much as the data are correlated with another variable that we can now take account of. And so analysis of covariance takes this variation, partitions some of it to the regression, leaving a smaller amount that is truly unexplained. So much better to use analysis of covariance when you have a covariate than analysis of variance. And you can see in the p-values that it had an effect on the p-value. Under analysis of variance down here in analysis 1, the p-value associated with group was 0.02. Now the p-value associated with group is 0.00161. And it's because the f-value has gotten bigger, but the f-value has gotten bigger not because anything has changed with the sums of squares. What has changed is the mean square value of the residual term, which is now 2.99, whereas it was 9.13 before. So now you're dividing 73.98 by 2.99, whereas before you were dividing 73.98 divided by 9.13. Your f value goes from a small but still significant f value to a much larger and much more significant f value, because you have accounted for the correlation between memory score and IQ. Does that make sense?
Yep.
Okay. Anybody else have any questions? Well, we could get fitted values. We can get the average values for analysis 2 in the same way that we've done it before. We can add those to our data frame. And now you see that these fitted values vary. Instead of y hat where they were all the same, y hat line basically has them varying with the correlation. So depending on what your value of IQ is, you have a lower predicted value than you would if your IQ is higher, where you have a higher predicted value because it's taking into account the linear regression. Well, we can take that value there and we can plot that as well. So we're just going to plot geom segment y hat line right there. And when we do that, it will show us now the line and presumably the residuals from the model. So in this script up here, I'm plotting IQ versus score. We're still coloring things by group. We're adding a couple of things. This is a segment that basically shows you the residual value, the difference between the IQ value, well, the score and the predicted values, and then it's showing you the lines. But these predicted values are not based on the actual lines. They're based on two lines that are parallel with one another. We haven't talked about analysis of covariance and the assumptions of the analysis of covariance yet, because we're just into our second day of it. But the assumptions are similar in some ways. The data are independent. They're collected randomly. There is a normality statement, so there is a normality assumption. In this case, it's the normality of the residuals, depending on which model you're using. There is a homogeneity of variances assumption, which we would normally test with Levene's test. But there is also an additional assumption in analysis of covariance, which is homogeneity of regression slopes. Analysis of covariance doesn't work unless these slopes are parallel with one another. So what we can do then is we can use the model of the analysis of covariance that is produced, and we can basically get the predicted values from analysis 2, which is our analysis of covariance. And when we do that, it will show us the lines parallel with one another. And then those residual values all meet up with the line. So now there's still a big residual here, but there are smaller residuals here, 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 and here. Really tiny residual values here because you have corrected these data now on the basis of the line. And so this is a common slope. It's the average slope of these two regressions. And this is what the analysis of covariance is doing, is it's asking basically, where's the grand mean? And then it's asking, if this is the average IQ score, if everybody in our study had the same IQ score, an IQ score of 115.8 or whatever it is, um, 115.2, sorry, 115.2. If everybody had an average IQ score of 115.2, what would their memory score be? Well, you get that by basically moving this point here along the line parallel to the line and have it reside at 115. You do the same for this guy, move him down, take this guy, scooch him down until they're all the same residual distance away from the line, but that line is no longer a line, it's a point at 115.2. You take all of the values for placebo, you drag them along parallel to the line to reside at 115.2, and then once you've done that, you ask, well, are these adjusted values different from these adjusted values? And you can see that that's going to be a much narrower spread of data down here and here than it is the spread of data from here to here in the memory score axis. And so one of the things that analysis of covariance does is it reduces the within sample variation, the residual variation, by accounting for the regression between the dependent variable and the independent variable of this regression. And that reduces the mean square residual value here, the sum square residual value, which then also reduces the mean square residual value, which then makes it easier to see the differences between the groups that are the thing that you're actually interested in doing something with. That makes sense to everyone.
So somewhere in the guts of this R code, it just does the averaging of those two slopes.
Yes.
We don't have to worry about it. It just does it.
You don't have to worry about that. It's just going to do it. And the process of doing that is complicated, which is why we're not going to work these by hand.
Okay, but it's all headed towards satisfying this assumption that there's this unique assumption to ANCOVA that there's this homogeneity of your regression slopes.
Yep.
Is there some point where those two slopes are just so different you gotta give it up?
Yes, there is. So one thing, a couple of things can happen. We'll end off here today, and we'll pick this up again on Wednesday, partway through the script. So if you have a covariate and a dependent variable, and for example, I need different color pens. The correlation between the dependent variable and the covariate for one categorical variable is like this, and the one for the other one is like this. because they're going in opposite directions, the amount of variation that is accounted for, it's going to just basically take all of these things and put them in the middle right on top of one another. And that variation is going to cancel out. But that variation is already being canceled out by the directions of these regressions. And so in this case, doing an analysis of covariance doesn't really gain you anything. There is another additional situation where you have, this is one of the ones covered in that chapter by Packard and Boardman. So you should really read that chapter by Packard and Boardman if you haven't already. But it's the situation where you have similar slopes, but the x-axis doesn't overlap at all. There's this hard cutoff. One of the other assumptions of an analysis of covariance is that you have a good spread of your values across the x-axis for both of your categories that you're comparing. This is not the case here, and it can sometimes lead you to the wrong answer as well. But those slopes were the same, but if you have slopes that diverge from one another in this way, also that's a violation, and it can in some cases lead you to the wrong answer. In many cases, because it's diverging, it's going to lead you to the correct answer, except that the average slope of this would be a flat slope. So it's going to adjust everything down this direction, and it's actually going to bring those things closer together rather than reveal their separateness. And so because the average slope would be the average slope of this line and this line, that's going to be a flat slope. That just basically cancels out all of your data. And so this is why the regression slopes assumption is pretty important. And on Wednesday or Friday, depending on how far we get, I'll show you how to test for that.
Okay, great.
All right.
Yeah.
And with that, we're out of time. Let me know if you have any questions about the regression assignment or the upcoming, well, the regression assignment, which is the only thing that's out there now. All right. I will see you guys on Wednesday.
See you.
All right.
Thank you.
Thank you.
All right. Bye.